Hey everyone, so I'm Sean Lilley from the Cesium team, and I'll also be covering what's new, but in this case for 3D tiles. So I joined Cesium in August 2015, almost 10 years ago. It was actually just after Patrick posted the Introducing 3D Tiles blog post. And so one of the first things I worked on was instancing, adding that to 3D tiles. And since then I've worked on a variety of aspects of 3D tiles, from the CesiumJS runtime to the Cesium tiling pipelines to the specification itself. So here I'll just talk about what we're working on and what's coming up next. So I think most people here are probably familiar with 3D tiles, but if not, 3D tiles is an open standard for streaming the built and natural environment. These screenshots show some of the diverse use cases, so from 3D buildings to point clouds, to photogrammetry, to vector data, and more. The common theme is that these are all massive geospatial datasets that require a level of detail and out-of-course streaming. So in 3D tiles, you have a tileset.json file that describes the spatial hierarchy, and then each tile in the tree references a GLTF, and the GLTF contains the tile's geometry, materials, and metadata. And then at runtime, you can use the metadata to style the tileset using our declarative styling language or custom shaders. So before I talk about what's new, I just want to give a quick history of 3D tiles. So 3D tiles was released as an open specification in 2015, and then became an OGC community standard in 2019. And then later in 2023, we published 3D tiles 1.1 as a revision to the community standard. And that added new features such as the ability to reference GLTF directly, implicit tiling for efficient quad trees and octrees, the ability for a tile to reference multiple contents, and then structured metadata at a variety of granularities, including per vertex and per texel. Since then, we've worked on a variety of new features, and I'll be covering pretty much each of these as we go. And a common theme that we'll see is that the GLTF ecosystem and the 3D tiles ecosystem are very closely connected. So because 3D tiles references GLTF for its tile content, anytime new extensions are added to GLTF, we kind of get them for free in a way in 3D tiles. So this includes like compression techniques like Draco, Meshopt, and KTX2. It also includes GPU instancing, PBR Next, materials, and more recently, Gaussian splats, voxels, and AEC rendering extensions. So Kevin touched on this. One thing we added recently to 3D tiles is an extension to define non-Earth ellipsoids. So we kind of did this to support the Cesium moon terrain release, but it's also relevant for other planets, other central bodies. And essentially, it's just you define what the central body is from a list of identifiers, and you also supply some explicit radii. And this is important because typically 3D tiles just defines a generic Cartesian coordinate system. It's often implicitly Earth-centered, Earth-fixed, but not always. So knowing what the actual central body is can be useful for certain applications. 3D tiles also now supports GPM 1.2. GPM stands for Generic Point Cloud Model. This is coming out of NGA, and it's for modeling the predicted accuracy of 3D surfaces. So what's interesting, especially about this extension, is it's modeling it at a per texel level. So in the video here, it's showing the vertical and horizontal predicted accuracy that's kind of encoded in a texture that's applied to the mesh. And the data is in a texture, but then you can query it at runtime, and you can also style based on those properties. And this was all developed in coordination with NGA and with Maxar for the Army One World Terrain program. And it's used in the well-formed format, which is built on 3D tiles. And next, kind of a huge deal for us, you saw it at the keynote, is Gaussian splats. So this is now fully supported in 3D tiles in a draft state. So we're still looking for feedback on especially the specification side. You'll hear more about Gaussian splats in the next talk, but it's essentially a new radiance field rendering technique. It does an excellent job of preserving fine details, and so you can kind of see the difference between the mesh representation and the Gaussian splat representation on the bottom right. So to add support for Gaussian splats to 3D tiles, we first need to add support in GLTF. So with Niantic, and Niantic created the SPZ format for basically compressed Gaussian splats. We worked on an extension together for GLTF called KHR SPZ Gaussian splats compression. And then this adds essentially additional attributes to a GLTF point cloud. So it has like the splat rotations, the scales, and the spherical harmonics for the specular effects. And all this data is packaged in an SPZ buffer, which compresses the data efficiently. So yeah, that's all I'll get into for now, because there's plenty more later in the next talk. So another thing is voxels. Kevin also touched on this. This is another alternative rendering technique. So it's typically for scientific data. We've talked about sort of this like underground material classification example, also ocean temperature. And we also built this prototype for showing density plots of satellites. And we used voxels to do the visualization for that. So we took a similar approach here. So we added an extension to GLTF first. And so because it's built on GLTF, we can leverage kind of all the existing extensions in GLTF, including MeshOpt, which is a compression extension. So we got essentially the uncompressed voxel data down, basically a 94% reduction in file size. And we didn't have to do anything. It was all part of MeshOpt. It was all part of GLTF. And we just got it for free by building on top of GLTF. And one thing that makes, I guess, our voxel approach unique is that we support a variety of shape types. So we support boxes, but we also support cylinders and ellipsoids. So it's truly designed for geospatial use cases. A lot of formats are just the box shape. So I think we have, yeah, very interesting techniques for how we do this. And so it's supported in Cesium.js. It's also supported in Cesium for Unreal as a pull request right now. And a key point is that we're doing like proper full volumetric rendering here. And like ray marching, it's not just rendering the voxel shells. So this is especially important if your data is kind of like this density plot, like the ability to see through it instead of just see sort of the block models is really important. We've also, I guess, looking now at the built environment, so I've been talking a lot about the natural environment. We have a pretty deep roadmap for architecture, engineering, and construction. So 2 GLTF extensions are in progress here. The first is primitive restart, and that's kind of a generic graphics technique that enables efficient polyline rendering. The second is an extension for defining edge outlines, like the screenshot here. And then on the roadmap are billboards, polyline materials, such as like dashed lines or line thickness, and then also the ability to control point size within GLTF. And then there's other features as well that are listed in this GitHub issue. Another area we're looking at for AEC is the process of formalizing how 3D tiles references semantic vocabularies. So for example, like BIS or base infrastructure schemas, IFC or industry foundation classes, Revit, OmniClass, UniClass. These are all data models in the AEC space, and we're figuring out how 3D tiles can reference those semantic data models. So, because it's especially important in the AEC space to carry over the full metadata and the semantics that are from the design model. So we want to make sure we don't lose any information when we convert to 3D tiles. And another big feature, something that I think kind of ties everything together in a way, because time dynamic data could be any type of data. It could be voxel data, it could be design data, it could be point cloud data, is this time dynamic 3D tiles feature that we're working on. So, and this is also personally what I'm working on right now, so it's top of mind. So initially our use case is for the earthworks industry, so kind of visualizing how a construction site changes over time. We're working with EarthBrain on smart construction to really optimize, especially large job sites, like job sites that have hundreds to thousands of daily collects of LiDAR data. And we don't want to have a separate tile set for each collect. We want to have a single tile set, but we want individual tiles to have a timeline, like so they have multiple contents that are time tagged, and we can easily step through time. And also, if just a small area of the site changes, we only want to have the multiple timestamps for those tiles. We don't want to duplicate data where it hasn't changed. So this is built a lot on 3D tiles 1.1. So it's built on the multiple contents that was added to 1.1. It's also built on either explicit or implicit tiling, but typically we'll have like a quadtree or octree as our data structure here, and we'll use implicit tiling. So there's one main extension for this, but there's 2 other supporting extensions. So expect to see those pretty soon, possibly by the end of the month. There'll be draft PRs in the 3D tiles repo. So, and also a Cesium.js implementation is in progress on a branch right now, but this should all be coming out pretty soon. All right, so I touched on this earlier, just this point that like the GLTF ecosystem is kind of driving the 3D tiles ecosystem, and we benefit from everything in GLTF. But I also wanted to sort of flip that a little bit and talk about sort of another thing that we're thinking about, which is how do we bring concepts from 3D tiles that might benefit the GLTF community into GLTF? So some examples of this are spatial subdivision, level of detail, and external references. GLTF right now is just kind of a single asset with materials, textures, geometry. But we're kind of thinking, how do we evolve that into complex scenes? So there's this new format that's being discussed called GLX, which is almost like an inheritance of GLTF. It has a lot of the same features as GLTF, like a very similar JSON schema, but it has the ability to potentially have external references, like a GLTF referencing other GLTFs, and the ability to specify a level of detail. So we've heard interest from people in the GLTF community about this, and we think it's a good opportunity to get some of the generic things that are in 3D tiles and bring them into the broader GLTF graphics community. So, and we'll talk about this more at the GLTF ecosystem forum tomorrow. And just a couple, honorable mentions of things that have kind of been on our mind for a while, which we haven't actively started working on them yet, but just wanted to mention them. So one is implicit geometry. So instead of, especially if you have AEC models where typically those are defined as implicit surfaces, like essentially equations of how the geometry is represented. Instead of tesseling that and turning that into triangles, we want to be able to carry over just those initial math definitions and then have the renderer do the tessellation, or have it be ray traced using SDFs or something. So yeah, one idea is to how do we represent implicit geometry in GLTF, and then how do we render that at runtime? Another thing that's been on the roadmap for a while is vector data. So I think a lot of this could be achieved with GLTF, but basically the ability to have points, lines, and polygons, and transmit that in a very efficient way. So like formats like GeoJSON are great, but often we want like a very compressed, efficient data format for this type of data. So we're always thinking about vector data and how to represent that and how to render that. And then finally, an archive format. So there's a couple existing archive formats out there, which you may have seen. There's like a .3D tiles SQLite-based format. There's also 3TZ, which is used in the One World Terrain program. And we're hoping to eventually standardize on an archive format. Maybe we will by the time we have like a 3D tiles 2.0. But for now, we just have a couple approaches that both, they kind of work, but we'd like to sort of consolidate them. I also wanted to touch on a few just high-level ecosystem updates. So yeah, this was also covered in the keynote, but I just really want to point out like the 3D tiles renderer in 3.js is really good, and there's been a lot of improvements lately. So this screenshot is showing like adding support for 3D tiles metadata, especially that per texel metadata that I touched on. And this was recently added, I think, in the past maybe half year or so. And it was through also a Cesium ecosystem grant. But yeah, definitely if you're using 3.js and you want to load 3D tiles, definitely check out this project. It's developed by Garrett Johnson, who I actually just met when I was in Tokyo last week. Yeah, it's just definitely worth checking out. And then just want to give a plug also for 3D tiles tools and the 3D tiles validator. So these have been, probably like 2 years ago, we made a major overhaul of these. And we're continuing to make improvements. So anytime new 3D tiles features comes out, we update 3D tiles tools in the 3D tiles validator. So you can just check that if you're either generating your own tile sets or using tile sets that you got elsewhere, the validator is a good place to try to just validate whether they're correct. So often it's a good place to go if you don't know if it's a runtime issue or a data issue. This is a good place to start.